The first thing we want to do is do an example of friction and forces with a rotated coordinate plane. So let's look at a situation where instead of sliding a box on the ground, we're going to slide a box down a hill. So let's put a box up here on a hill, and let's just say that we don't know the mass, so we'll do this generally. So we'll put the box on the hill and we'll let it slide down the hill. So why don't we make it a, just for easiness, 30-degree hill. So we're sliding a box down a 30-degree hill, and we want to know what the acceleration is of the box as it goes down the hill. So step one, always our step one is find a coordinate system. So the coordinate system in this case, remember that we always want to have the box, one of our coordinate planes moving in the direction of the box. So in this case, the box is going to slide down the hill. So what we're going to do is we're going to have one of our coordinates follow the hill, and then the other coordinate obviously has to be perpendicular to that, so it's going to be perpendicular to the hill. So in effect, we've got a coordinate plane that started out this way, right, if it was flat, and we've rotated it to match the hill. Alright, so this is a rotated coordinate plane. X will follow the hill, Y will be perpendicular to the hill. Alright, so first step is done. We have a coordinate plane, X and Y, and it's rotated so it follows the hill. Second thing we're going to do is we are going to draw our free body diagram. Free body diagram for the mass, let's just put our mass right out here. That's our mass, and the forces are mg. mg is straight down towards the earth. And then the normal force is obviously perpendicular, so it's up in this direction perpendicular to the hill. So there's the normal force and there's the mg. So mg and normal force, and just to remind us, I'll put our coordinate system x and y. So we know this, that the Fn is in the y direction and the mg is actually in neither. It's not in the x or the y, so the mg is going to end up giving us problems as we go along. So we have our coordinate system, we have our free body diagram. Now we need to write down our equations of motion. So the sum of the forces in the x direction and the sum of the forces in the y direction. Well, like I said, this Fn is obviously in the y direction, so we're going to have Fn positive here. But this mg gives us problems. It's not in x or it's not in y. So we're going to have to break that up so it's in a coordinate system. So let's break that up so that it follows one of the coordinates. And what we'll do is we'll just make it follow in the x direction and in the y direction. So we'll say mg goes in this direction, in the y direction, and over here in the x direction. Notice that I followed my coordinate system. One of them has to be in y, one of them has to be in x. I need to draw that triangle carefully so that each of those is in one of the coordinate planes. And now we have a problem. mg is the hypotenuse. I need to know an angle in this triangle in order to figure out what the direction is. Let me just redraw this larger, and let's see if we can figure out that angle. So we'll come back to this in a second. So here's going to be a little bit of an aside. Let's draw this nice and big. Here is our angle, here's our mass sitting on the slope, and we know that this is a 30-degree angle. Alright? The free body diagram, we said that mg pointed straight down. Right? And what we did is we broke that mg up into something perpendicular to the hill and something parallel to the hill. And what we're trying to do is we're trying to figure out, because this was our coordinate system, x and y, we're trying to figure out, do we know one of these angles in the triangle? Well, as you can see, that's actually pretty easy. This is a 30-degree angle. This is a 90-degree angle because mg is straight down. So if this is 30 and this is 90, that means that this angle up here has to be 60 degrees. Alright, so we have a 30, 60, 90 triangle here. We also know that because I drew this component, this y component is a y component perpendicular to the hill, we know that this has to be 90 degrees. So now we have a straight line here We have a 90-degree angle and a 60-degree angle, which leaves this top internal angle to also be 30 degrees. Notice that this 30 degrees matches the 30 degrees of the hill. So we now have this little triangle. We have, if we want to redraw our free body diagram, there's our MG, and here was our box up here, and we have our coordinate system, X and Y, and we broke this down into coordinates, X and Y, and this is a 30-degree angle. This one is going to end up being MG sine 30, and this is going to be MG cosine 30. So we end up now being able to find the components of MG in our free body diagram. Alright, so you can follow that. Let's go back to our original picture. Here is our original picture. I don't know why it got so dark all of a sudden. I don't know if you can still see that or not. Oh, there we go. Okay, so here's our original picture. And we're looking how to break up this coordinate system right here. So we ended up, like we said, MG is the hypotenuse, so this is going to be my 30-degree angle. So we have MG sine 30 and MG cosine 30. So I'm going to now be able to put those into my equations. Notice that in the x direction is my MG sine 30, MG sine 30 degrees, and in my y direction, even though it's downward, so it's negative y, is going to be minus mg cosine 30. That's all that's going on. In the y direction, plus fn, and minus mg cosine 30. In the x direction is just mg sine 30. So I'm done with that. So equals max equals may, and now I can think about what's going on. I've done my coordinate system, I've done my free body diagram, we played a little bit with the angles so we could figure out the components of mg, and then we wrote down our equations, and now we can think. In this case, since the box is sliding down the hill, we're going to end up with only motion in the x direction, so like we've been doing, the acceleration in y is 0, and I can say Fn minus mg cosine 30 equals 0, or Fn equals mg cosine 30. And that's the best I can do until I know what the mass is. And if I knew the mass, g is a number, cosine 30 is a number, but for right now, since I didn't tell you the mass, that's the best I can do. All right? What about this x equation? Right? I can take this equation right here. Let's just put it down here. Mg sine 30 degrees is equal to mass times acceleration in the x direction. In this case, we'll notice that there's a mass in each term. So this mass and this mass can disappear, and we end up with acceleration in the x direction is equal to g sine 30, or since g sine 30 is 9.8 times sine 30, acceleration in x is equal to 4.9 meters per second squared, I believe. Yeah. Okay, so we end up finding the acceleration, and notice that it didn't even depend on the mass, mostly because maybe I didn't mention no friction. If there's friction, then, well, we'll have to think about that in a bit once we figure out what to do with friction. So we end up with an acceleration of 4.9 meters per second squared. Now we can ask any sort of kinematic question. We know the acceleration of this thing. We could say, let's imagine that this hill is 100 meters long, and it starts at rest. So we could say, let's do a kinematics problem. Let's say that we have V0, VA, T, and delta X. Notice that we're only doing things in one dimension because the box is only moving in X. Nothing's going on in Y. start this thing at rest, move it for 100 meters, find the acceleration. The acceleration we said was 4.9 meters per second squared. Now we can find the final velocity, find how much time it takes to get down to the hill. Doesn't matter, right? If we wanted to find the final velocity, v squared equals v0 squared plus 2a delta x. So it's going to equal to 0 plus 2 times 4.9 meters per second squared times 100 meters. So that's going to be v squared equals 980 meters squared per second squared, or v is equal to plus or minus. Since I take the square root, I always get a plus or minus. Square root of 980 is 31.3 meters per second. Now I have to decide which am I choosing, plus or minus. I can go back to my picture and realize, oh, I'm going down the hill, I'm going forward in x, so I'll say v is equal to positive 31.3 meters per second at the bottom of that 100-meter hill. And if you wanted to, you could also then find the time using v equals v0 plus at or some similar kinematic equation. All right, so just to review, step 1, find the coordinate system. Step 2, free body diagram. Step 3, write down the equations of motion. And then step 4 is think. The equations of motion, writing them down, required us to break down the mg since that was a rotated coordinate system. So that's a problem with a rotated coordinate system, and I will now move on to friction.